Hi everyone, I would like today to talk about an interesting family of problems, and those are called dispersion problems. And typically those relate to facilities or services, whatever, that are not really desirable. Okay, we don't really want them near where we live. And in fact, they are an interesting set of acronyms that you can find in the literature. I'm just going to point a few of them. Not in my backyard, or the NIMBY effect. Banana, which stands for build absolutely nothing anywhere near anything. You have other funny acronym like SUBY, so it essentially stands for some other burger's backyard. So things you don't want to have near you, but sometimes you actually need those. And let's look at a few examples of those undesirable, let's put it this way, facilities. For instance, low-income housing development. Typically, this is something that people don't want to have too close to where they live. There is actually some disagreement about this one, bicycle pedestrian infrastructure. So the idea initially was you didn't really want to have, let's say, a bicycle lane in your backyard or near your backyard, to kind of may bring some lot of people, and you don't really want to want that. But there's been enough literature that has shown that, in fact, having a bike lane near where you live may actually increase the price or housing price. Or the value of your house if that's where you live. Things that people generally do not want to have are military base, but then there is again the aspect of, okay, this may bring jobs, and the same goes for prisons or jails, right? You don't want to live close to a prison. Incinerator, generally there is not a whole lot of support in communities for that, because it's not just the fact that it's not good for the environment. You may have actually an impact very close by if you have fumes coming your way. Recycling center, that's again a little bit the same as the others. People don't want it because not only it generates a lot of traffic to get all this waste, but then people think, oh, maybe that's actually quite useful. We actually need it, right? So there is here this sort of duality. Nuclear waste site, I have never heard someone who was in favor of that. Sex offenders, communities can be very worried about that. Cannabis shops also, maybe, because it brings a lot of tourists, different kind of tourists, and people don't really want to see that. Youth hostel, for instance, something that is very popular in the politics is abortion clinics. Some people may argue here from a political standpoint that things like a Planned Parenthood, for instance, may provide other type of service than just abortion. Okay, maybe we actually need them. Okay, cell towers. Okay, so this is something very interesting. Some people are not in favor of cell towers near where they live because they think maybe the sort of, based on the wave and the signal that it propagates, maybe this could lead to cancer. There's not really a lot of literature confirming this. However, it's quite useful to have a cell tower not too far from where you live because you use the service. In fact, in some countries, an example in Belgium where churches can decide to put towers, not cell towers, but maybe base stations, basically on top of the churches, and then they would get actually money every year for that as a sort of a rent. Homeless shelter, something that, or immigration, shelters, migrant shelters, things that people don't want that either. And then there is an interesting component here, and these are stores. So maybe a store, like maybe a chain, say like a McDonald's, Subway, Wendy's, and so on. They may not want to have another store nearby. They may want to try to locate as far as possible from existing store. So the same approach can be used there as well. And I just want to show us a very small example here where, just need my chalk, we may have here a geographic area, we have population here, and we need to decide on where to locate a new landfill. Now, right, so maybe a possible solution may be here. I hope you're going to be able to see it. Maybe here's a solution, maybe one here is here, and maybe one is right here. I can guarantee you that the majority of the population will say it will be here. Okay? Now, if this was a cell tower, there might be a chance that this might be closer because people need the service, right? They don't want this in their backyard, but they need the service. So this is sort of a duality here. Before we move into the formulation of these dispersion problems, I just want to try to build a few thoughts on how we actually going to formulate these problems. Okay, so that will be our next step. Before we move into the formulation, we can think about the dispersion problem as follows. It's essentially to try to find the maximum weighted number of facilities and their locations such that no two facilities, right, are within a stipulated minimum distance or time threshold, or if you want a sort of minimum separation of each other. And this example here can be taken, for instance, for fast food. You may have a subway chain here, you may have another subway chain here. In order to avoid market saturation, you may want to spread them quite far from one another. Okay, so here I like to spend a little bit more time also to think about this from as the book from Rick Church and Alan Murray suggests here in the case of harvesting, right? Sometimes when you harvest like a timber harvesting and others, you may want to disperse the activities so that if you harvest something, then around it stays the same, and then you can harvest again. So if we were to harvest unit 2 here, right? So this is the one that we're going to harvest. Okay. So that would mean in that case, take another color. If we don't want the adjacent parcels to be harvested, right, we would basically say, okay, well, this cannot be harvested, this cannot be harvested, it's actually adjacent, this one neither, this one is also adjacent neither, this one neither as well. And so that would leave us essentially then with the next possibilities, right, that probably is going to be 10. And also going to say, okay, 10 may be harvested here, okay? Okay, but if 10 is harvested here, then 9 of course cannot be harvested here, okay? And then that may leave us, for instance, maybe 7 to be harvested here. Okay, and then 8 cannot be harvested in this case. Is this the optimal solution for 3? Maybe not, maybe we can do better. But you can see here, how do you define this sort of separation? Could either be in distance, could also be in form of adjacency that we can easily calculate within a GIS. And so our next step really is to come up with this interesting formulation of defining, okay, what is considered adjacent, what is considered too close, okay. So let's look at that formulation now. Okay, I'd like to go into the formulation now. So we have a new index here, which is I, and it's the index of potential facility sites. There is also index G here, which is basically similar to that one. This for other facilities, we'll talk about this in a second. And then we have this new variable, A sub ij here, and it's equal to 1 if, I forgot actually to add a 1 here, so just do that right now. It's equal to 1 here, sorry about that. If I is too close from G here, so those two facilities are too close from one another, and 0 otherwise. So this works kind of the same as we were doing before in the proximity. I remember where we're looking at the proximity of a demand node from a facility. Same approach. The GIS can be used here quite easily to populate that value here. Phi sub I, that's the set of all the facilities such that A sub ij is equal to 1. So set of potential facilities that in fact are in conflict with I. That's another way to define it. We have B sub I, which is the benefit to locate at I. In the case of a facility that we don't really want in our backyard, I don't really know if there is a benefit to it, but in the case where you have, for instance, two fast food that are locating as far as possible from one another, for instance, or they want to try to maximize maybe the benefits. The benefit can again be calculated maybe with a coverage, or how much population is live nearby. So that of course is subject to discussion here. What is not subject to discussion is the decision variable x sub I, which is equal to 1 if we locate at I and 0 otherwise, and that sort of together give us kind of the direction of the objective function, which is trying to maximize the benefit of locating facilities. Now, one thing that is important, right? So, okay, we were going to use this as the sort of main objective, but it's sort of looking at what restrictions do we want. We have talked about, you know, things, facilities want to be separated as far as possible. Maybe those can be achieved through neighborhood restriction, maybe pairwise restriction, and clique restrictions. In the next short videos, I'm going to focus on neighborhood restriction and pairwise restrictions, okay? And hopefully that will clarify how we define our set of constraints. All right, as I mentioned, we had the objective function, but we can look at different restrictions. One of them was the neighborhood restriction, and one is the pairwise restriction, and one is the clique restriction. We're going to focus on the neighborhood restriction, and actually, what does it mean? So we essentially have this constraint here, n sub I, x sub I, plus a summation here of all the facilities that are in conflict, right? X sub j should be less or equal to n sub I. And what is this n sub I? N sub I here, and you can see here these two lines here, these vertical lines, right? It's actually the total number of facilities j's that are in conflict with I. So we want to keep track of, given I, if we want to locate in I, which are the facilities that cannot locate near I, and vice versa. If we were not to locate in I, then all the facilities around I may be actually available for siting. And we take these two examples where we say, well, what happens if xi is equal to 1? If we locate it at I, then this here, so this as ni should be less or equal to an ni, and then by definition here, this should be equal to 0. So if we locate it, in I, I'm just showing you here, right? I don't know if I have some space, maybe here, okay? So if we locate here in I, okay, we know that there is a bunch of facilities here around, right, in that distance threshold, and those are the j's, so j equal 1, j equal 1, 2, j equal 3, and we know we cannot locate at these different facilities because of the neighborhood restrictions. Okay, if we do not locate at I, then that means that all of the other facilities around it can be selected, okay? And I say here, none of facilities j in proximity of I are prohibited from being cited, okay? So that is this neighborhood restriction constraint. And then if you put this into the objective here, the entire formulation here, as you can see here, okay, we have the same objective function that we had before. We're adding this constraint, and now we have this. So quite frankly, this is not a very complicated formulation. The only problem is that you may want to pre-calculate here which facilities are in conflict with one another. That's where, again, GIS is quite useful. So now we're going to spend time on the other one, which is the pairwise restriction. The second type of restriction that we have is pairwise restriction. And the idea here is that if you, again, I mean, kind of the same idea, if you locate at I, you cannot locate at J. Okay, that's pretty obvious. And how can we capture that? Well, we're going to introduce this new constraint here, but pretty straightforward, right? X sub I plus X sub J should be less or equal to 1. And here what essentially it means that if we were to locate at I, we wouldn't be able to locate at J. And again, J's are all of these, I mean, we could do it for all of the facilities that are around I within this sort of distance threshold, okay? And likewise, if we were to locate at J here, then Xi, right, would be equal to 0. So here you can say if Xj is equal to 1, then Xi is equal to 0, okay? That's the idea of the pairwise restriction here. And then if you were to just, follow the same formulation that we had before, here this is our formulation, and this here would be the constraint that is included. Again, because this comes from this phi sub I, very, very easy to do within a GIS, or at least not very difficult to estimate that. And then you can run this, through Cplex and see the solutions here. Okay, so that's on the sort of dispersion models, but there are two other things I'd like to discuss. We'll do that in another video, and this is the maxi-min problem and the maxi-sum problem, where we're trying to basically locate facility as far as possible from existing population to maximize the distance, okay? Unless, unlike when we do in a p-median, if you want, it's kind of the opposite which was to minimize the sum of the distances. Okay, well, I hope this was useful. And as I have said, many of these comes from this book here, written by Rick Church and Murray, and I highly recommend you